Hi everyone, welcome to the short tutorial on compound interest. This is a little extension of the work we've done so far on power functions and exponential functions. So let's get straight in then. 100 euros is invested in an account at 5% compounding interest. How much money will be in the account at the end of 5 years? So we're going to put into the account 100 euros, 100 pounds, $100, it doesn't really matter. And we're going to increase the amount in that account by 5% every year, multiplying by 1.05. At the next period, we're going to take all of this amount and we're going to multiply it by 1.05 again. So now we've got 2 periods. What we can do then is take all of that and multiply it again by 1.05. And clearly we're going to do that another 2 times to get to the 5 years. So I'll just add those numbers on the end there, 1.05 times 1.05. The important thing to notice here is that the 100 hasn't done very much, it's sat there, and the only thing that's changing is these numbers are being added on each time, multiplying it through. So the answer to our question is that after 5 years, we are going to have 100 times 1.05 to the power of 5. 1.05 multiplied by itself 5 times. And when we take our calculator and put that number in, we get out of the system a total of 127.63. So by leaving your £100 alone for 5 years at 5%, not adding or taking away and not changing the interest rate, you would expect to have 127.63 in your bank account. And you can choose different numbers for your percentages and different numbers for your amount invested and calculate it all exactly the same way. Now the flip side of that is an interesting idea. What happens when you have got the following problem? Once again, we take 100 euros, whatever, invested in an account at 5% compounding interest. How long must the money be in the account so that it reaches a value of 200 euros? Okay, so this is like a flip question. Now we don't know how long it's going to be invested for, but we do know how much and what the increase is going to be each time. So this time the question looks a bit like this. We've got 100 and we're going to multiply it by 1.05 some number of times. We're trying to find out what that number is. So it's 1.05 to the n, and we want it at the end to be equal to 200 units, dollars, euros, yen, whatever. Okay, so this we've seen in our little piece of work on exponential functions and logarithms. We can solve using logarithms. We can rewrite that equation, 1.05 to the n equals 200 divided by 100, which is equal to 2. And from there, we can take logarithms of both sides. And if we take the log 10 of both sides, we get that n multiplied by the log of 1.05. If you're not sure why that's true, go back and look at the little bit we did on logarithms, is equal to the log of 2. And when we rearrange, we can get n is equal to the log of 2 divided by the log of 1.05, which we can write out as 0.30103 for those of you who remember the log 10 of 2. I do that because I'm a bit strange. And we need the logarithm of 1.05. Okay, and when you got the logarithm of 1.05, the answer to that is 1.05 logarithm. It's 0.02 119. And when you process that, you get an answer equal to 14.2. So what does that mean? 14.2 years when you're paid once a year. Well, that means that the target of 200 is achieved somewhere above 14 years and below 15. So we had 100 multiplied by 10 to the 14, which when you do that calculation gives you the sum of, let me just find that number, 197 and something. And then the other one, 100 times 10 to the 15, gives you 207 and something. So that's true. We arrive at 200 somewhere between 14 and 15 years. And you might choose that 197 is close enough and stop there. Or you might want to go on and add a little bit more. So I hope you found those two little things useful to help you solve some of the problems. Thank you very much. I'll see you again soon.